I'm going to go over, like, well, not every single problem, but yeah, I'll cover all the bases. Which problem you're interested in? Yeah, I'm definitely talking about that one. Okay, so, all right, now problem one is not really worthy of comment. That one went well, very well, actually, generally speaking. And, okay, so not much to say there. Really nothing to say. Number two, not much to say on that one either. That one went well. I think there's one very common mistake, because I think just about everybody, or almost everybody, got to this point where you have, this is fx at the given point, and then fy at the given point, some change in y, and then this is fz at the given point times the change in z. Almost everybody wrote down this, except there's one little thing here that's missing. Equals 0. A lot of people forgot this, and no, I did not take off many points for that, but it still deserves a deduction, because what do you ask for? The equation of a tangent plane. It's not an equation without an equal sign. All right, so what I saw in this test are a number of certain fundamental things like this that come from some sort of lower level class, whether it's an earlier calculus or something below that. If you're asked for to cough up an equation of something, that's something that should be automatic. Because that's what that means. That's what an equation is. And this happens a lot that people kind of know the terms, but they don't really. But where else in other than math is precision more important than here? So again, not a big deduction, but it's things like this, sloppiness like this, that ends up causing larger point losses in other things. Okay, problem 3. Function you were given this one. Now, I find it troubling that people who demonstrated such skill with partial differentiation on problem 1 promptly abandoned that skill on this one. So derivative with respect to x. So what did seem to register, again, any mistake I point out, if it's a mistake that like one person made or something, I'm not going to talk about it here. But anything I talk about here is going to be because a number of people did it, enough to really register like, wow, this is a trend. If you're differentiating with respect to x, what have I said from the beginning? Y is treated as a constant. Therefore, this whole thing, cosine pi y, is treated as a constant, a multiplicative constant. Therefore, it just stays there. So any differentiate this part with respect to x. Some people forgot their chain rule. But this is what you get for that. And then that constant just stays there. That's all in a number of derivatives, a number of cases where this was tossed out. If it was added, sure, but not when it's multiplied. That's another thing that pops up all the time. Even at classes at this level, not remembering what happens for addition versus multiplication. A lot of the root causes of mistakes are simply getting both wires crossed. And you can't afford to have that happen. So with that in mind, what should Fy be?
E to the negative x squared.
Yes, because that part is now the constant.
Sine pi y.
Yeah, minus. Yeah. Okay, and then what's left? Times pi is the chain rule. Yeah. Okay. Now, people, for most part, seem to understand in general what to do with these partial derivatives and how to construct a formula for linearization been evaluated at a given point. There weren't really big problems there, but this is where the one big problem was. And here's another. When plugging in the point, x equals 1 and y equals 1/4, we have e to the minus x squared. That is e to the minus, you do the squaring first, and then you negate. A lot of people wrote e to the first when they plugged in the point. No, it's e to the minus 1. So it works like that. It doesn't work like that, where you negate first and then square, because what does this simplify to? Well, yeah, it's e to the x squared. So,
Wait.
what?
That's definitely what I meant.
Okay, yeah, okay. Yeah, so in other words, if it meant this, then why would we have a minus at all? So this has to be kept in mind. Exponentiation, okay, this is straight order of operations. Exponentiation that gets applied before negation, not after. Okay, so that caused some smaller point losses. Okay. Now, the linearization in general is you evaluate the function at the point. Some people forgot that part of it. And then, with respect to x, plus derivative with respect to y times, so each derivative gets multiplied by the corresponding change. Okay. Also, since this involves a trig function, so since y is being plugged in there, make sure your calculator's in radians. There's some answers that got that suggested that your calculator was in degree mode rather than radian mode. And in fact, I can tell you how you can be tipped off that your calculator's in the wrong mode. Because if you are in degree mode, but what you should be in, and at this level of math class, unless let's actually see the degree symbol somewhere in the problem, you should be in radians. So if you're supposed to be in radian mode, but your calculator is actually in degree mode, here's how you can tell. And it turns out that cosine will always give you answers that are really close to 1. Why? Because what are radian values? They tend to be small, between 0 and 2 pi. So if you take a number that's between like 0 and 6, and interpret it as 0 to 6 degrees, that's a small angle. Cosine is small angles, it's always really close to 1. And sine would always be close to 0. So if whatever you plug in is always like really, really close to 0 for sine, or really, really close to 1 for cosine, that's your tip-off, that your calculator's in the wrong mode and you need to change it. All right. And that's how I could tell that some of you were in that situation. Now, is there any questions about this problem? Now that you have your work back. But again, the main problem we solve is with system of differentiation. I don't know the situation where people get thrown off because there's exponential function and a trig function versus polynomials like in the first problem, but the rules are the same when it comes to partial differentiation. You differentiate with respect to one variable and then holding all the others constant. Just because it's a different kind of function doesn't mean all of a sudden things are done differently. They're not. If you think of any questions, we don't have it right now, but if you think of them later, of course, you can ask them. Okay. Certainly the remaining 3 problems are also worth talking about. Number 4 was the chain rule problem. And most had the general idea right. So you ask for dz du and dz dv. So dz du would be dz dx dx du plus dz dy dy du. Now, and in this case, x is u cosine v, y is u sine v. There are two common problems that I spotted with this in this case. First of all, problems with differentiating v's. Again, here we're differentiating with respect to u. U is what you're differentiating with respect to. V is held constant. So what should dx du be? Just cosine v. I got some strange answers that had like two terms in them, like you're using product rule or something. Yes, this is a product, but if you're only differentiating with respect to u, this is not a product rule situation. This is treated as constant, so is sine v, and therefore dx dv, sorry, not that, dy du would be sine v. So these are just linear functions of u. So so this is like you're taking a derivative with respect to x of 2x and you get 2. It's the exact same situation. It's just that the constant in question is really a function of v. But v is being treated as a constant. So it's important that you recognize that these two situations, though they appear to be different, are really exactly the same. What about dx dv? Now u is the constant. Come on. Yeah, so sine v becomes, cosine v becomes minus sine v, and then the u remains as a constant. It's multiplied, so it's not added, so it sticks around. And therefore, dy dv is going to be similar. Yes, u cosine v. Okay. So those were what goes into these pieces, and then dz dv is similar. So dz dx dx dy dv plus dz dy dy dv. Okay. So these four derivatives get plugged into these spots, and then dz dx dz dy get plugged in the appropriate places as well. The only other common mistake, and this was again a small deduction, because you're differentiating, you're thinking of z no longer as a function of x and y, but as a function of u and v. Therefore, your answers should be in terms of u and v only. I got some answers that had u, v, x, and y in them. As a last step, after you do all the differentiation and put all these in here, as a last step, you're supposed to replace x and y with these functions of u and v. So your answer, your final answer, must only be a function of the inner function's independent variables. Is there any questions about that one? Number 5, directional derivative. Now, it's at times like this when I start to seriously contemplate no longer giving practice tests. Because people do something, they just blindly repeat what was on a practice test. The practice test is meant to give you an idea of what types of problems will be in the test. There's still going to be differences, and you need to be aware of that. This is also an issue of problem 6 that I'll get to in a moment. Okay, so what I said, my exact words here, was u has the same direction as 1 minus 1. What does it mean when two vectors have the same direction in terms of the components. What that means is u is parallel to this vector, or in terms of the components, you could say that u is equal to this vector times a constant. All right, so when two vectors have the same direction, and in fact we can say a little more than that. Not only is there a constant that defines this relationship, we can also say the constant is positive. These are things that you learn in Cal 3 that become important in Cal 4 and any other class that uses vectors. That this kind of phrasing is something, and this is why prerequisites matter. It's phrasing that you should understand what it means. Yes, when I gave this problem, it did occur to me that people would just do this on a practice test and said, I'll just blindly do that, not paying attention to the fact that there's different directions this time as to specifying u. And I figured, well, if I lay it out like this, u has the same direction as this, that if you understand vectors, you know what that means, and we'll do the right thing. And that's why if you simply did what was on a practice test and just took the 2 points that were given and subtracting, not paying attention to what those points really meant, but you did not read the problem carefully enough. But you otherwise worked the rest of the problem correctly. I only took off 3 points in those situations. And if there were other mistakes, then there'd be a larger deduction. So I didn't make a big deal out of it, but I put this on here and deliberately left it in here to see what would happen, and as a wake-up call to you guys, that you need to pay closer attention to these details. There is no success in math without paying attention to detail. And in this problem, that did not happen by and large. So what that means is, and now from what you also are supposed to know about directional derivatives, u has to be a unit vector, and people almost unanimously knew that. So u would be this vector divided by its magnitude. Okay, this is why I wrote on the board, read period the period dang period directions period. So then you go ahead and take the gradient vector and take the dot product with this. So any questions about this one?
You said you only took 3 points off of that?
If the problem was otherwise done correctly, just using the wrong, now what happened in some cases was people were subtracting taking 1 minus the given point 3, 2, and then divided by its magnitude. So if you did that and did everything else correctly, that's only 3 points. But some people made a mistake in doing this or a mistake elsewhere. Of course, if you're not sure where you lost points, you can always ask me about it afterwards. Any other questions? Okay, so this is something to keep in mind. For future tests, you need to look more closely at this, and also understand what the verbiage means in these different situations. And finally, problem 6. Most understood the general idea that you take the partial derivatives, you set them equal to 0, find critical points, and then you classify the critical points, as maximum and saddle point. But algebraically, things went awry. Okay, so your fx in this problem was 2x minus 6y, and you set that equals 0. and your Fy is minus 6x plus 20y minus 2. You set that equal to 0. Now, I was a bit alarmed by how many people somehow came up with 4 critical points when there's only 1. And the problem from a practice test had 4 critical points. Now, if that, what happened on a practice test, led you to believe that there must be 4 critical points this time, if you made a conclusion based on that, in spite of a mountain of evidence to the contrary, for instance, other examples being worked in class that did not have 4 critical points, homework problems, for which reason why we rescheduled a test to give you time to do that homework, which also could have any number of critical points. You could have any number of critical points in 0, 1, 2 on up. That there is no, if you made a conclusion based on that, then you're taking the guidance from a practice test in a totally wrong way. I hope it's not what happened. Maybe it's just an honest algebraic mistake. But the fact that there was a noticeable number of people somehow certain that there were 4 critical points and coming up with them in ways that would totally offend the laws of algebra, that's cause for alarm for me. And so I'll show you what happened here, and in the hope that this sort of incident doesn't repeat. Because these 2 equations, you have to find x and y that satisfy both of these simultaneously. And this is similar to another problem that I recall doing in class, where these equations are both linear in x and y. So you do elimination and substitution. And in cases like this where they're linear, you're generally going to have a unique critical point. I thought, oh, well, that'll save you guys time. If you're only having to work with 1 critical point instead of 4, so what you can get from these equations, you can simplify this one and you get x equal to 3y. Now, that doesn't give you values of x or y specifically, but at least it gives you an easy relationship between them that you can now substitute in here. That would give you minus 6 times 3y plus 20y minus 2 is equal to 0. And then you can go ahead and simplify this as best you can. So you get 2y is equal to 2, so y is equal to 1. So from taking both equations into account, the only way to make both of these equal to 0 is for y to be 1. Then you plug that back into here and conclude that x is equal to 3. So the only critical point is x is 3 and y is 1. And a number of people did come up with that critical point. And then they came with other ones. And admittedly, I did not take the time to try to decipher from the work that everyone wrote what led them to these critical points. In a couple cases I did. For instance, I saw a case where this was reworked after y was discovered, or actually after x was discovered to be 3, that was plugged back in here, which would just give you back y equals 1. But then if a mistake is made, then you end up getting a different value. I saw some people considering a case where x equals 0 or y equals 0. And that made me wonder if there's a misinterpretation of what's in the practice test. The practice test had the possibility of x equals 0 or y equals 0 in those critical points. But let's go ahead. Okay, I'll plug in x equals 0 or y equals 0. So if x equals 0, then you have minus 6y is equal to 0, so therefore y is 0. So for fx, you must have y equals 0. But then you go ahead and plug in x equals 0 in the second equation, fy equals 0, and you get 20y is equal to 2 and therefore y is equal to 1/10. And I did see numbers like these in some of your work. So let me explain why this is flawed. So what the conclusion is fx equals 0 if x equals 0, y equals 0. Okay. And then fy equals 0 if xy is equal to 0, 1/10. But the thing is, neither one of these points will make fx and fy equal to 0 simultaneously. And that appears to be the problem. That you may have thought, some of you may have thought that if you got a point that would make one of a partial derivative 0, that would be enough for a critical point. So this is the only point that makes fx equals 0 and fy equals 0 simultaneously. That's what I said from the beginning when covering this topic. Both partial derivatives must be equal to 0 at a critical point for it to be a critical point. Okay. So any questions about this one? Okay. Generally speaking, there is no compelling reason to think that x equals 0 or y equals 0 is a case worth exploring, unless it's like a problem in a practice test where you could factor an x or a y out of these. Then, because if that's the case, when you have an equation set equal to 0 and you can factor anything out of it, then of course you should consider whether that should be equal to 0. That's a good idea. But something like this, you couldn't factor anything out of this. Either one of these. Like here you could factor out a 2. That's all you got. So here also you could factor out a 2, but what does that really get you? So, so factoring is always a good idea to try. But if you don't get a factor, if somebody doesn't get a factor, then there's generally no point in setting that equal to 0. So don't just automatically look at, oh, x equals 0, y equals 0 is a possibility. Follow where the actual algebra takes you. Right, so, and unfortunately, this is what the pain about these problems or Lagrange multiplier problems from the following section. That is, each situation is different depending on the functions that you have. There is no recipe for this. You just have to use whatever techniques you learned over all these years, ever since you first started taking algebra, to try to figure things out, and not go off the rails, and because that's what I saw a lot of here. Okay, so that's the conclusion of my rant. Are there any questions? Okay. I feel very fortunate at the age of 47 to not have any gray hairs, but I think they increased on Friday. I hope there won't be a significant color change between now and the end of the semester. So we'll see what happens. Okay. And yeah, certainly if you have any questions about the test, you can always ask me after as well. Okay. I mean, so no, these were not bad tests, although, I mean, considering the scores. But also, I do give partial credit. If you did everything right, but you only made a sign mistake, that's generally that's going to take off a point. If it's otherwise, you generally knew what you were doing, but made a small mistake, probably tests like this take off the 3 points. And then if I took off more points, it's because you displayed less understanding of what you were supposed to do. And if I don't really see effort, like you hardly write anything down at all, then you're hardly going to get any points at all. Okay. Now, during the time I have left, we can start the next chapter. You've done all this partial differentiating. Now we'll get into integrating. Now you can dust off all of your Cal 2 knowledge. Okay. So as a quick review from single variable calculus. If you're integrating a function f of x on some interval a, b, so this is a definite integral, and we need a dx here. So for general f of x, you need to define a function which I'll call big F. And you plug the endpoints a and b into it, subtract it. But this function big F, what do we call this? Function big F is a what of little f from Cal 2? We could call it like the indefinite integral. What's the other term for it? Starts with an A. Antiderivative. Yeah. So big F is antiderivative of little f, meaning that big F prime is equal to little f. And you learned all these integration rules, integration by parts, substitution, partial fractions, things like that, to try to be able to compute antiderivatives in as many situations as you can. Now, the fact that you can evaluate this integral of little f by finding an antiderivative and plugging in the endpoints, instead of what you learned at the beginning of Cal 2, presumably, working this out by taking a Riemann sum and taking a limit of a sum of areas of rectangles. Since you could just do this statement right here, that the integral was equal to this. I don't suppose anyone knows what that statement is called. That says you can do this.
Fundamental theorem.
Yes, this is the fundamental theorem of calculus, or at least one part of it, the part that we're interested in. The other part of it goes the other way. That this basically says that integration cancels out differentiation. The other part of the theorem goes the other way around, that differentiation cancels out integration. So it's the same relationship. And actually, I should mention that although much of calculus is credited to Isaac Newton, the person who first recognized the inverse relationship between differentiation and integration was not Isaac Newton, but Isaac Barrow, who was Newton's teacher. So, teachers rock. Sorry, I just had to throw it in there. Now, before we could talk about several variables, what is the interpretation of this integral? Like geometrically, what does it mean?
It's the area under the curve.
Area under the curve. So we have a graph, my generic curve here that you'll see often, y equals f of x between x equals a, x equals b, and the region bounded below by y equals 0, that the area of this shaded region is the exact area given by the definite integral. That's why integral calculus, we learned in Calculus 2, is so important, that instead of only being able to compute areas for simple situations, like with rectangles, the integral lets us use formulas involving products in more situations, like generalizes area equals width times height, or other formulas involving products like distance equals velocity times time, or mass equals density times volume, as I mentioned at the beginning of the semester, I believe. Okay. No, actually that was in Calculus 2, but I was substituting for. But you all needed to hear this too. And really the integral is defined as what you would get if you took infinitely many rectangles of this kind, where the width is delta x, and the height is given by f evaluated at some point. You can approximate this area using however many rectangles you choose. But what happens if you take infinitely many rectangles? That involves a limit. So the integral is actually defined as a limit of using infinitely many rectangles. But you don't need to do that. You can just do this. Okay, so that's what happens in single variable case. So what happens if you have functions of two variables? What does it mean to integrate a function of two variables? both how do you compute it and also how do you interpret it. And I have 10 minutes to tell you. Because in two variables, we're stepping up by one dimension. Just as we went from tangent lines to tangent planes, if a single variable integral gives you an area, if we add one more variable, we're going up a dimension. What do you think we're going to get this time? Volume. Yes, that's exactly what happens. So a double integral so geometrically what's happening is you have some region, and at first we're going to use the simplest region possible in two-dimensional space, a rectangle. So here we have x equals a, here's your x-axis, y, z. Here's x equals b, and then the rest of a rectangle is defined by y equals c and y equals d. So this rectangle, which I'll call R, is a Cartesian product, a to b in x, and the interval c to d in y. Now, suppose that over this rectangle you have a function z equals f of xy. So I've plugged in points from this rectangle into my function f, and I get some sort of surface patch. So this is z is f of xy. Okay. So instead of computing the area under the curve, the volume under the surface. So everything moves up one dimension. Instead of area under a curve, it's volume under a surface, defined by z equals f of xy. And more precisely, I'll say it's volume of a region bounded by x equals a, x equals b, y equals c, y equals d, z equals 0, z equals f of xy. So now, instead of having 4 boundaries, like the region there, you're often going to have 6. Now, I say often, not always. It depends on how the region is defined. So you have some well-defined region in the xy plane that has certain equations defining whatever boundaries, and then you're integrating computing volume between z equals 0 and z equals your function. And that volume is given by the double integral of f over a rectangle R. So single integrals were over an interval, double integrals are over some sort of two-dimensional region. Today we're talking about rectangles. Later this week I'll move to more general regions. So how do you write this? Use two integral signs. And it's customary to indicate whatever region is if you give it a label like this R down below, and f of xy. And instead of simply writing dx, I often write dA. A is an element of area, whereas dx is an element of length. Again, everything moves up one dimension. Now this is how the integral is often written down, except the way it's written down here doesn't really help you to compute it. We want to use the fundamental theorem of calculus, just like we could of single integrals. So I'm going to write this in a way that lets you do that. So I can write this as a single integral from a to b dx. So this is my outer integral. And then here we have another integral from c to d in y. Now, a and b are x values. They correspond to the dx. C and d are y values. They correspond to the dy. And you plug f of xy in this as your integrand. So you could think of this as you're evaluating an integral with respect to y first. And then you do just like single integrals. And you plug in limits c and d. Now what's left is a function of only x. Y has been taken care of. And then you do that integral. So this is called an iterated integral, because you're evaluating a double integral by breaking it down into two single integrals. And often you can use either order. Here, you integrate with respect to y first, or you can integrate with respect to x first. And when you're dealing with a rectangle, you can always do that. You can pick whichever order you want, whatever's convenient. In other regions, it's not so simple as that. So both of these are iterated integrals. And the justification for doing this is called Fubini's theorem. Because the double integral, this volume, was not defined using single integrals at all. It is dealing with volumes of boxes. Instead of infinitely many rectangles over there, you think of this as infinitely many boxes over here, where the base is in this region R, and the height is determined by f of xy again. So the definition of a double integral, in terms of, like, again, limit of a Riemann sum, does not let you do this. It's Fubini's theorem that lets you do this. So I'm going to use the last few minutes here, so don't pack up yet, to do a simple example. Double integral from x squared y plus xy cubed dA over rectangle R. It goes from 0 to 1 in x. The first interval listed is always x. And then 0 to 2 in y. So I can write this as integral from 0 to 1 dx of integral from 0 to 2 dy of my function. So how would I actually work this out? You start from the inside and work your way out. So you integrate with respect to y first, and what you get is x squared, because that's a constant. It's just like partial differentiation, but in reverse. Y squared over 2 plus x, y to the 4th over 4, with limits 0 and 2, and these are limits in y. So you plug in these values in for y, and, dang it. Okay. And when you plug in those limits, what you get is details are in the notes, page 2x squared plus 4x dx. So you plug in if you plug in y equal 2 in here, minus what you get from plugging in y equals 0, it simplifies to this. Now I can integrate with respect to x, and that's going to give you 2x cubed over 3 plus 4x to the 4th over 4. No. Yeah. Sorry. Limits 0 and 1. And then you plug those x values in, and the final result that you get is 8/3. Okay. Now, again, look at the notes. There are more steps in here than what I did here, just because I want to show you this before we quit today. But we're going to keep doing this all week long for rectangles and general regions. But just remember, you're integrating with respect to one variable at a time, and then all other variables are treated as constants until you get to the point where you integrate with respect to those. Okay. Oh wow, I had a minute to spare.